Okay, let's start our meeting. Welcome everyone to the Astronomical Society of Edinburgh. My name is Mark Phillips. I'm the president of the society. And this is what we've got happening tonight. We've got a few slides from ourselves, first of all, but our guest speaker this evening is Dr. Martin Elvis, who's in Cambridge, Massachusetts at the moment. And he's going to talk to us about asteroids, how love, fear, and greed will determine our future in space. So that sounds really fascinating. Looking forward to that one. Won't hold you up too long, just a few things to cover first of all. We have a few new members of the last couple of weeks, Alan Jones, Francis, Ron Morley and Susanna Rowland. If we could all unmute and welcome them as normal. And that brings our membership up to 154, which was quite a dramatic rise over the last year and a half or so. And just a reminder that our membership fees are very modest, £30 for normal, and concessions are £15. And just a little reminder to our members that your renewals were due at the start of this month, unless you joined on or after the 1st of April this year. Then you don't need to renew till next year. We have lots of ways of staying in touch with us through our website, our Facebook page, Twitter, and our YouTube channel has all the videos of all our meetings over the last few years on it. And there's been some amazing talks on there, and this one will be no different. This will be on afterwards as well. So it's a good place to catch up and see what's been going on with us. Over the next few months, we've got some more interesting talks lined up. So at the start of November, the first Friday in November, we've got Dr. Justin Campbell-White from the University of Dundee telling us about accretion disks of stars. That will be a hybrid meeting, so we will be in the Augustine United Church on George IV Bridge in Edinburgh, but we will always plan to stream our talks online on Zoom for our members and on YouTube for visitors. So you're always welcome at those. And Alan Pickup will be telling us about the sky in November in his usual comprehensive way. And on the 10th of November, we have our imaging and observing group. That's for ASE members only. That is a place where we all learn about imaging and observing together. And we've had some amazing meetings recently, and we do learn a lot from each other. And a lot of great images being taken at the moment by members. On the 19th of November, we have David H. Levy telling us about his life in astronomy and all his discoveries and what he's done in his life. And on the 3rd of December, our own Will Joy will be telling us about finding space rocks. So hunting meteorites and what that means. Again, that's a hybrid meeting in Edinburgh and online. The 17th of December, an online meeting about Thomas Cook, the telescope maker, which is relevant to us since we've been very involved in the Calton Hill Observatory, where there is a Thomas Cook telescope. The first meeting of 2022 is with Dr. Rebecca Higgett, who's the Curator of Science, National Museum of Scotland, and one of our members, and she'll be telling us about Neville Maskelyne. So a good lineup. We have other talks lined up for the rest of next year as well, but keep an eye on our website for more information. But that's it from me. So over to Dr. Martin Elvis in the USA to do his talk. I'll just stop the share, Martin, and that's over to you now. And you're muted, Martin.
Unmute. Okay. Can you hear me now?
Yes, we can. Thank you.
Okay. Excellent. Thank you. Good evening. Very pleased to be here. And I've changed the title slightly. Since this is an astronomy society, I've termed this not only how love, fear, and greed will determine our future in space, but also the future of astronomy. So let me explain. Oh, right. I've just spent a good long career in investigating supermassive black holes, some of the most energetic and distant phenomena in the universe that we can study. And yet I've now moved into asteroid work. So pretty much the closest, smallest things you can work on and still be an astronomer. So why would I make that change? So this is my motivation for getting started. You may not think so, but I believe astronomy has a crisis, a long-running, slow crisis. We've become very used to being able to look at any part of the electromagnetic spectrum. So from the far infrared with Herschel, the normal infrared with the Spitzer Space Telescope, the optical and ultraviolet with Hubble, and out into the X-ray band with the Chandra X-ray Observatory. And they've been working all very well together for almost 20 years. We've had this coverage. Herschel was a bit shorter lived, but now we've also lost Spitzer, and Hubble and Chandra are very old, 20 years old or thereabouts or more. And this way of working between different wave bands has changed the way we do astrophysics. So 21st century astrophysics, as the band Nada Surf, I'm sure you're all fans, pointed out, the stars are indifferent to astronomy on their album. And it's true, the stars, galaxies, quasars, all these things emit their radiation where they will. They don't pay no attention to us and are the limits of our humble, feeble technology. So in order to understand what's going on, and here are a couple of classic examples of multi-wavelength, multi-band observations coming together to make a true understanding of what's going on in something. This is the bullet cluster, if you want to, with the red being X-rays and the blue being the dark matter in this case, as measured by lensing, strong lensing. It's essential to do astrophysics this way. We're so used to it, and yet it's going to go away. The James Webb Space Telescope just arrived for launch at the site in Kourou in French Guiana. Should have been the first of a new generation of bigger, better, great observatories spanning the electromagnetic spectrum. But as is all too well known, it cost $10 billion or thereabouts. And at that rate, NASA at least can only afford one every 15 years, and ESA is not in a much better position either. And the worst thing is, unlike the great observatories we've been used to, James Webb will run out of fuel to maintain its halo orbit around the Lagrange point. And so it will not be usable after, well, nominally 5 years, and we hope it will stretch to 10. But that's much too short. There will be no time to launch even one other flagship like Great Observatory in time to match it and be operating simultaneously. So instead of making an observation with Hubble and the next year following it up with Chandra, you will have to say, oh, I made this great James Webb discovery, but I have to wait 15, 20 years to follow it up with a new X-ray or far infrared observations that will make me, it'll give us the true understanding of what I've discovered. That's not going to be a very interesting field compared with our golden age that we're in now. Now, we could always double or treble the budget. That would be the nice way to do it, of course. Oddly, that seems to be implausible. People don't seem keen to treble the astronomy budget, at least in the United States. And so there won't be a new generation of great observatories if we go on like this. The party's over, unless we can find a way to drive down the costs. And so it's pretty obvious that's how I got into asteroid work. That may take a little more explaining, and so that's really what the rest of the talk is about. Why asteroids? We have, like any whodunit, I'm going to divide the talk into 3 parts: motive, means, and opportunity, and we'll see each one in turn. So let's start with with a quick primer on asteroids, just so we're all on the same page, and it's going to be horribly oversimplified. But first of all, planets not to scale in this diagram of the solar system. All those green dots are real known asteroids in the main belt between Mars and Jupiter. There's about 1 million known currently, but they're all large, and so there's many, many more smaller ones we can't yet detect. And a few tens of thousands have been kicked into orbits that come closer by to the inner solar system. Those are the red dots there. These are called near-Earth objects. Some of them come near the Earth, some of them cross the Earth's orbit, and of course, historically, they have collided with the Earth. These are the near NEOs, objects rather than asteroids, because a few of them are dead comets, and it's a little hard to know which is which. Now, the asteroids come from the early solar system, the breakup of planetesimals in the early solar system, which were the first objects to form, from which some of which combined together to form the planets, and others which had faster impacts and broke up into smaller pieces, which produced the asteroids. Now, these planetesimals are up to about 1,000 kilometers across, a few hundred kilometers across, certainly. And that meant that the radioactive heating in the early solar system was enough to melt their interiors. And that meant they differentiated, just like the Earth. So they have an iron core, nickel iron, which takes up a small amount of the volume. And those led to the metallic meteorites and asteroids. Surrounded by a silicate mantle, this is just normal rock, taking up most of the volume, and that led, when they break it up, that turns into stony asteroids, and of course meteorites that are similar. And then on the outside, or perhaps more from smaller planetesimals that didn't really heat up enough to melt particularly, you get a crust of carbonaceous rock, of the early primitive material of the solar system. And when that's broken up, you get carbonaceous asteroids and meteorites. And when we say carbonaceous, it doesn't mean slightly enriched in carbon and organic molecules. It means really, really pretty solidly. If you slice a piece off the Allende carbonaceous meteorite that fell to Earth when was it? Quite a few decades ago now. If you take a fresh slice off that and smell it, it smells like asphalt, like tar. So it's really rich. So that's the background information, the 3 types of asteroid that we are thinking about. So what are the motives to go to the asteroids? They are love, fear, and greed. And those are good motives for doing a lot. Well, they're certainly motives for doing a lot of things. So let's talk about asteroids and love first. And I admit it, it's a cheat, because I'm talking about love of knowledge, which is perhaps not what you were hoping. But asteroids are involved in at least 4 big science questions. They seem big to me anyway, and that's up to you to make your own decision. First, asteroids are great clues to the history of the solar system. There's a model called the Nice model for the city in France where it was originated, which talks about how asteroids were crucial in changing the architecture of the solar system. They kept getting scattered by Jupiter, hundreds and many of them. And of course, those asteroids got deflected into orbits that flung them inwards and also out into the outer solar system. But the asteroids, over time, one by one, slightly changed the orbit of Jupiter and gradually moved both Jupiter and Saturn into a resonance, and then rapid changes happened. So the asteroids were crucial to that process. And at a certain point, Saturn's orbit became highly elliptical, and that would scatter far more asteroids, and they led to a bombardment of the inner solar system, Mars, Earth, Moon, at least, with a whole rain of asteroids hitting them. And that is used to explain the cratering history on the Moon, which appears to show a peak just a few hundred million years after the solar system first formed. Some of those scattered asteroids also end up becoming Trojans, or the irregular moons of the gas giant planets. There's a mission going to investigate the Trojans that will be launched very soon. And whoop, there we go. Asteroids today are still very interesting because they are the things that have not really changed since their last major interaction, at least. So they can be used to test the history of the solar system. That's why we're sending a mission to the Trojans. Second question, asteroids and the Earth's oceans. Where do the Earth's oceans come from? We live on this ocean planet. And one idea is that there shouldn't be oceans on Earth, like just as there aren't elsewhere, because the Earth was molten, and it's surely hard to retain water in a molten rock planet. And then it solidified, and then you have to provide water. So the leading idea is that asteroids or comets brought enough water to the Earth to make the oceans, and it would happen sometime after the collision that remelted the Earth and created the Moon. Now, we're not really talking that much water. It's 1% of the Earth's mass. And so when you put that in the cosmic context, the solar system context, it's about 5 times the amount of water in Ceres, the largest asteroid, the first one to be found, and perhaps the nearest thing we have to a planetesimal still remaining in the solar system. So only a few of these large planetesimals needed to have collided with the Earth to provide us with the oceans that we have. How do you test this idea? One method is to look at the deuterium to hydrogen, the heavy water to hydrogen ratio, heavy hydrogen to hydrogen ratio. And so far it looks like asteroids are a better bet, a better match to Earth's oceans than, say, the comets. There's a very accurate point in yellow there, or gold, whatever you think they call it, from the Rosetta mission, which provided this slide. What about the origins of life? Of course, that's a very big question, but maybe life was helped along by enriching the primordial soup, by bringing prebiotic molecules along with the water during that same late bombardment that brought the water of the oceans. We know that meteorites contain amino acids, many amino acids, sugars, and more complex organics. There's a record setter that so far as I can tell, is this one on the left from a husband and wife team at Harvard. And they're continuing to search for more. So it gets this could have been could sped up, or maybe even totally facilitated the origin of life on Earth. A lot of the delicate asteroid material is lost by the heating of re-entry. Asteroids break up, small asteroids break up before into smaller chunks. 90% of the mass is lost, and only a tiny fraction reaches the ground, the hardest piece, the most resilient to heating. And so we're losing a lot of material. And maybe some of that would have arrived on large bodies that impact the Earth rather than the small things that we deal with most of the time now. So if there was other material there, organic material, we could find it if we could get samples of asteroids of the carbonaceous type. And so, of course, that's one of the big motivations for Hayabusa 2 and OSIRIS-REx to go out and pick up samples, which they've done, and return them to Earth, which so far Hayabusa 2 has done, but OSIRIS-REx is taking longer to come back. If anyone works on exoplanets or thinks about them, there's a little question that I popped in there. And then the last question is, why are there iron mines? We need iron to have a technological civilization. We need access to metals, particularly iron. But iron sinks very efficiently to the core of the molten Earth, taking with it a lot of what are called siderophile elements, platinum, palladium, gold, that melt into, to dissolve in liquid iron. And so that's a very efficient process. There should be essentially no iron left in the Earth's crust. And yet there are large deposits. Here's one, an iron mine in Western Australia, one of the biggest going. Perhaps asteroids brought that iron after the crust formed. And this would have actually had to happen just before the late bombardment I talked about, just in the tail end of the accretion of rocks and material that made the Earth. Oops. And this, there is evidence for this based on tungsten and isotope ratios and others too. So it's a promising idea, but we don't know much about this yet. The second motivation is fear. And of course, this is something everybody's heard about. This is a map of the solar system around Earth in Earth-centric coordinates. So the Earth is that blue little circle in the center, and its orbit is the cyan stripe. And you see all the known asteroids whizzing by as time goes by, and we're counting days here. You can see on the little clicker at the bottom. And we don't know all of them. There are many more than this. We also know that an asteroid killed the dinosaurs, and we don't want that to happen to us. Actually, it's a very strange thing, but it killed most dinosaurs, but not the avian dinosaurs, which are birds, that were ground dwelling and had beaks. And those, for some reason, survived, and all the others didn't. And there's some speculation on that as to why. It's actually mentioned in my book. I had to go into it a bit. But anyway, of all the things that could kill off humanity totally, this is the only one we could actually prevent by deflecting the killer asteroid on its way in. Now, the good news is we've found 90% of the potential dinosaur killers, that is humanity killers, which are bigger than about 1 kilometer across. There are 900 or so known right now, but there's still 100 left, and it only takes one. So it'd be very wise to keep searching for those last 100 and to make sure we are not taken by surprise. On the other hand, city killer asteroids only need to be about 20 meters across, so a big house, really big house, I suppose. A mansion would do. You see the one from 1908, Tunguska, famously leveled an area about the size of a large metropolitan area, in this case, Washington, DC, for example, just to give scale. And there's one of those every few decades. The ones we know about in the last 100 or 200 years are listed there. If you're in Russia, I would begin to feel persecuted because it's getting to look suspicious. Not really, but that's a funny thing about statistics. This is probably an incomplete list. The Wabar craters were large when they were first described in the 1930s, and when a group went back in the 1960s, they found out that they've been filled in by the sand of the Saudi Arabian desert, and they were still there, but hard to find. So this may well be others that landed in places that did not leave a record. I'm going to attempt something now which will probably fail, but we'll see. When death rains from the skies, what do? Obviously, we all run and scream, but no, we don't. Let's see if this works. Here is, can you see this? This is documentary evidence of an experiment. Let's hope it works and get the right thing.
That face.
No, it's the wrong thing. Never mind. That'll teach me.
It's just an advert, I think. Just need to wait.
You think so?
Yeah.
All right, I'll let it go. There was no ad when I
made an
started.
appearance. That face wouldn't be doing that if you weren't staying at a Virgo lake house. You're together awaits.
Oh, skip
Find
out.
it with Virgo.
There we go. Here we are. Chelyabinsk, 2013. Dash cam. There goes the line. So you all sense the panic in everybody's voices there, and how they all ran screaming and actually totally ignored the thing in the sky. There's another one where people just walk across the street casually without even looking up. It's amazing. There we go. And finally, asteroids and greed. Greed is a powerful motivator for many people. And it's been said by an awful lot of people, beginning, I think, with Peter Diamandis, that the first trillionaire will be an asteroid miner. Well, maybe. First of all, you have to think about this a little more seriously. And this is actually where I got into real analysis about asteroids and so on. I got annoyed by some of the early claims. And so I looked into some of the numbers involved, which make me a lot more skeptical. There are three things being talked about: platinum, water, and iron that you could measure, that you could mine from resources in the sky, from asteroids, basically. Platinum is certainly worth a lot, $50 million a ton. That's great. Water and iron aren't worth much on Earth, of course. Some very fancy designer water if you have to get that useful price. But in space, if you had someone to sell them to, they're worth at least $1.5 million a ton, perhaps double that, based on the costs currently. But the problem is that in space, no one can hear you sell. There's no customers in space for you right now. So it's a chicken and the egg. If there were customers, we could mine. And if we could mine, will there be customers? We don't know. So that means we have to get to how we're going to do this if we're going to satisfy these motives we have, strong motives for dealing with asteroids. So the first thing is finding all the asteroids. And there's two big surveys coming up, just about to start. The Rubin Observatory is looking at reflected sunlight, so normal optical light, in its legacy survey of space and time. And they, according to a paper I read, will be finding 3/4 of the modest size, 100-meter or bigger asteroids, near-Earth asteroids. So that's sort of a football stadium size. And they'll also give us the colors of these asteroids. And because there's a very clear red absorption feature in stony asteroids, it'll tell us which ones are stony, which is most of them. So, and they're probably not very interesting for many purposes. That's going to start next year and go for 10 years. But that is going to make it, that survey looking at reflected sunlight is not very good if you want to find the carbonaceous ones that contain a lot of interesting materials. Luckily, we can use their black body emission, and because we're looking for near-Earth objects, they're at much the same temperature as the Earth, so about 300 degrees Kelvin, absolute. And here's what a person looks like at in the wavelengths where that emission peaks, around 10 microns. This is Ned Wright, actually. He's the principal investigator of an infrared mission, which is why he has this picture taken. And there's going to be a new mission from NASA just to find the near-Earth objects, particularly motivated by fear, by finding the ones that could kill us. And they will find 90% of the ones bigger than 140 meters across. Connecting the numbers at the same sizes is a little tricky. And because black body emission scales with the area of the object, you can actually work out its size quite accurately this way. So you get the size, you get the colors. If you combine the two, you work out, you can measure the albedo of the asteroid. And if it's very low, meaning a few percent, even 1%, it's very dark. It's darker than freshly laid tar or a clean blackboard. Those are very likely to be carbonaceous. So you learn quite a lot. You can pick out the carbonaceous and the stony, and that doesn't completely solve the problems, but it gets you a long way. So by 2030, 2032, we'll have a huge, complete catalog down to the size of 100 meters-ish. And that will help with all three of the motivations for going to the asteroids. So how are we going to study asteroids? Well, there's a new enthusiasm for asteroid missions. It's fair to say that asteroids were pretty much ignored in the first few decades of space exploration, planetary exploration, because the planets were much more attractive. And of course, they were fabulous to go visit. But now there's this realization of the importance of the asteroids in solar system history in particular has led to Hayabusa 2 going to the carbonaceous asteroid Ryugu, OSIRIS-REx going to Bennu, Lucy, which is being launched tomorrow, is going to the Trojan asteroids and visiting, I think, 7 of them. And then Psyche, which is going to, confusingly, Psyche, 16 Psyche to differentiate it, is going to launch in the middle of next year. And Psyche is famous for being the biggest metallic asteroid that we know of. And at least we're pretty confident it's metallic, sure hope so. So it's a whole new type of world that we've never been to. And it's the first time we can sample the core of a planet in any sense, because it's been exposed for us. And then that's the love. Now the fear. How do we deal with an asteroid threat? The truly reliable way is to use gravity. Gravity never turns off. It's always there. It's kind of weak, but it does work. But the idea is you put as massive a spacecraft as you can find, as you can build and send out there to one side of the asteroid and keep pulling on the asteroid, either speeding it up or slowing it down in its orbit until it's changed its velocity enough that when it reaches Earth's orbit, the Earth is no longer there as it would have been. Much simpler, just punching it on the nose. And this is called a kinetic impactor. Again, the biggest and fastest mass you can launch. That's another mission called DART, Double Asteroid something mission. Launches in November. And the idea is that it will hit the smaller of a binary member of a binary asteroid, the moon of Didymos, originally called Didymoon because they needed a name. It's now called Dimorphos to be much more polite, but I like Didymoon. Anyway, so it'll take about a year to get to the asteroid, and will strike Didymoon and change its orbit by millimeters per second. And that will is enough, however, to measure its to change in its orbit as it goes around the Didymos, the main asteroid. That's why they chose a binary asteroid. Or if you want to get really serious, you could go full Bruce Willis on them and nuke the asteroid. And people at Los Alamos have been studying this. They have a vested interest, of course, but I'm sure they're accurate in what they do. And that will impart far more energy to the asteroid and so slow it down more than any kinetic impactor. The problem with kinetic impactors is you probably need several of them to slow down any reasonable sized asteroid, and they all have to work. And if one of them was the first one accidentally split the asteroid in two, what do the others follow-up ones do? Can they head for one or the other, or have you missed out on the whole slowing down thing and you now get two impacts on Earth? So that's a motivation to send a nuke. Trouble with the gravity tractor is you probably need 20 years of warning. I already talked about the multiple hits that all have to work for the kinetic impactor. And the problem with the nuke is maybe it will just shatter the asteroid rather than slowing it down. This is, on the left is a picture of a meteorite being hit with a bullet moving at 6 kilometers a second, which is the right sort of speed. And it completely shatters, breaks into smithereens. Obviously, to get this right, we need to practice on some asteroids like DART is doing, only even more so. And we need to do it safely, so only on asteroids that are never going to hit the Earth, even if everything went wrong with our experiment. And then greed, that's the first thing you need to do if you want to sell asteroid material, is find the resource-rich asteroids. You have to go prospecting. Now, if you're going to do it remotely, one of the favorite things to do is look for water, because it could be an easy early product to sell in space. The problem is on the ground, the absolute best location in the spectrum to look is at 3 microns in the infrared. And for those who know about this, that's the K and L bands. And there's a gap between them due to absorption in the atmosphere, which is right in the wrong place. As you can see, these spectra of bright asteroids show a dip that somehow is minimum at a minimum somewhere in that band that we can't observe. And they're bright asteroids because in the L band, 3 microns or so, the sky is very bright. And it limits us to only the biggest, brightest asteroids. So we can't do a lot of prospecting from the ground. But a pretty modest space telescope would actually be a lot more sensitive than a big telescope on the ground. So there's a mission, an infrared mission from ESA called Ariel, which I think is being led out of University College, London, which is doing pretty much the right thing. The problem is it can't track moving objects, and there's just no way to do that. I've talked to the PI and she says, no, sorry, Gov. So maybe NASA could have a follow-on to its NEO surveyor and that would do this. Or, and here's an interesting idea, maybe there's a private company that would like to do this to profit off the intellectual property that would come as a result of all this prospecting. They would have a list of the best water-rich asteroids, and they could sell that to mining companies. And there's maybe a good example of how you might do this is the Twinkle satellite, which should be launched in a few years, which is a private commercial venture, which is selling data on exoplanets. I don't think it can track moving objects either, but there's a similar, but it is much cheaper than Ariel. And hopefully we could build a copy and add a capability to track moving objects like near-Earth asteroids, and that might lead to a commercial venture in asteroid prospecting. Let's think about how we would actually get the material out of the asteroids. We've got platinum, water, and iron. So platinum, well, it's worth an awful lot, and there is a market on Earth. And it's actually useful stuff. It's rather not like gold, but there's only 30 grams per ton, even in the richest meteorites, and so the richest asteroids. And that's a lot of extraction work, and you have to do the extraction out at the asteroid's initial orbit, its native orbit, because you can't move large masses around the solar system for no profit. The rocket equation is horribly against you at this ratio. So it's a hard thing to do at such a distance, and it requires a lot of energy. So this doesn't look to me at the moment very promising. Water is a lot better, 100 kilograms per ton, 10% water. It's quite easy to mine. You heat up the asteroid and the water will steam off. It's not in solid water ice form. It's mostly bound to clays and OH bonds, but as you heat it up, you make water and collect it. Iron is the easiest. The metallic asteroids are pretty solid, but pretty much solid nickel iron. With very little else involved, and as in this example meteorite on the left. So it's 1 ton per ton, and it's pretty easy to mine. You just cut the size lump you want, and then ship it back. So in principle, you could possibly undercut the cost of water or iron in a geostationary orbit, where the energetics are even more favorable to you, and possibly even in low Earth orbit, where most of the market is likely to be. But what is that market? Well, first, I want to show you that the water, knowing where the water is valuable. Here's an analysis I did of how many asteroids, what fraction of all asteroids are rich in water or platinum. And the answer is a few percent. And that doesn't sound too bad. There's another estimate that maybe that 3% of water should be 6%, but it's pretty uncertain. Probably better than my estimate. The biggest problem is that of all the near-Earth asteroids at the moment, with the rockets we currently have, we can only reach 3% of them with a large payload, that is about at least a ton. And that means the total number is very small. I put this into a little equation, which new scientists kindly called the Elvis equation. I like that idea. Nobody else seems to have picked them up on it, but that's okay. if you look at it, you can see it's a ripoff of the Drake equation for how many civilizations there might be in the galaxy. But the numbers here are much better determined, certainly than they used to be in the Drake equation. But the number turns out to be maybe a dozen, maybe 2 dozen. And so knowing which those are is incredibly valuable intellectual property. That number will increase as we get bigger rockets, and maybe the SpaceX Starship will change this into a number more like 200 or 300. We'll see. Okay, more about prospecting, excuse me. Given the probability of something being a rich asteroid for water or whatever, how many asteroids do you need to investigate to have a good confidence of seeing one? Well, this is an exercise in binomial probability, and I did it with a student, Thomas Esty, some time ago. And basically, 1 in 4 carbonaceous meteorites is water rich, and you just look along here to where 0.25 is and read off the number of asteroids you need to investigate, and it's between 10 and 20. So you have to send out 10 probes to find one good candidate with decent chance of being right. That means they've got to be much cheaper. The OSIRIS-REx cost $1 billion, so no way. I know Hayabusa 2 cost, I think, more like $200 million. That's still much too much. You can't fly 10 of them. We have to get down to $10 million, $20 million. And to do that, to have a successful interplanetary mission at that size and cost, you have 3 big challenges: propulsion, communications, and navigation. Com and nav, as the cognoscenti say. Well, there are promising solutions to all of these. I'll mention navigation later on, but suffice it to say that it's very plausible that we will soon have ways of building such spacecraft. Whether they can be built quite at the cost we need, I don't know. Better prospecting remotely would allow us to have fewer probes to send out to prove the resource, the ore body. So I'm betting that the first attempts to bring back resources from the asteroids will begin somewhere around 2030, maybe a little later, but in that ballpark. And then we're talking about rare and valuable real estate, like oceanfront, beachfront real estate. And that always leads to extra legal activities, especially when the law enforcement is weak, as of course it is in space right now. So I teamed up with an ethicist, Tony Milligan at King's College London, who lives near Dundee most of the time, I believe, and Alana Krolikovsky, who is a policy expert, and we talk about these issues. So we think about 4 different things that could go on: spying, claim jumping, rustling, and piracy. And under current outer space law, which is basically just the Outer Space Treaty, it's surprising that espionage is pretty much encouraged in the sense of a promoted openness. Claim jumping is totally legal because there's no mineral rights that you can have over any celestial body. Rustling is pretty certainly legal. That would be where you found out that someone has identified a resource-rich asteroid. You get there first, you attach a little rocket and change its orbit. And space is big. It's going to be very hard for anyone else to find that asteroid once you've moved it. But you know where you moved it, into what orbit you moved it into, so you can find it and you can go and exploit it. So you're basically making use of somebody's intellectual property. And the one thing that's not allowed, definitely is illegal, is piracy, where you capture the refined ore out of a spacecraft that's on its way home, because that spacecraft does still belong to whoever launched it. And more countries are saying that if you picked something up from an asteroid and carted it home, it's yours. So as was punned some years ago by Scott Irvin, we're dealing with law in a vacuum here. Sorry about that. Okay, but there is really no one who adjudicates disputes over these space issues. And it's going to be a field where, unfortunately, we will need to start getting getting serious about legal and policy requirements. Probably diplomats will be involved, who knows. So the opportunity is really section now. Why motive means an opportunity. We've got to opportunity. Why are we doing this now? Well, there was the motivation that astronomers need these new, bigger telescopes, but that doesn't affect most people. What's really changing is this new space movement, which is mostly now epitomized by SpaceX. Their advertised price per kilogram to low Earth orbit is $1,600, so £1,000 more or less. That is a fifth of what it was before they started work. And they're hoping with the Starship to bring that down at least another factor 5. Even if they don't get quite that far, an order of magnitude decrease in cost to orbit makes it, is transformative. It's not just launch though. There are efforts now for on-orbit refueling of satellites. There's the Northrop mission extension vehicle has done that twice. There is also standardization coming along. Orbit Fab is a startup, and they are having great success selling a standardized fuel cap, basically, that you allow that allows all satellites to be refueled with the same technology, same connectors. So things are moving along, and an in-space economy seems to be really starting up. Let me explain what I mean. That all these resources are worth nothing until you have a customer, but now maybe there are customers starting up. We've seen suborbital and orbital tourism. William Shatner went to suborbital flight just the other day. A little before that, there was the Inspiration 4 flight to orbital, to orbit the Earth for 3 days. Tourism is beginning, and at the moment, it doesn't need any resources from space, but it's going to grow. People are going to want to stay longer and in space hotels, and that's coming along, believe it or not. There's also research, which is being done on the International Space Station, but it's not being done by scientists on the International Space Station. It's being done by astronauts who are trained up, and they're very clever, but they each have to look after a lot of experiments, of order a dozen, and they cannot be experts in all those fields. And so the normal interaction by which you do research and learn from mistakes and learn from seeing things you didn't expect, that's going to be much improved as we get cheaper access to space. And okay, people can go to space at a reasonable price. And thirdly, there is a push to, sorry. What I'm showing on the left is actually a company called TechShot who are practicing, researching the printing, 3D printing of organs, of cells into complex organs, and hoping eventually to be able to print a human heart. And so that would be a wonderful breakthrough for a lot of people who suffer from heart disease, but also, at least from a US perspective, that's a way of making a lot of money because that heart is worth an awful lot to the person involved. And so the fact that you have this less than a kilogram of heart mass to take down from orbit, the fact that you're doing all this in space can become unimportant in the cost. Manufacturing also has some high value products being developed that are very promising. Very many, I think 3 companies are experimenting with this optical fiber called ZBLAM. It's a fluoride based thing. And when you make it, in principle, it would be 10 times the bandwidth of the optical fibers we now use, and would not need repeaters even across the Atlantic Ocean. So it'd be cheaper and higher bandwidth, and that would enable so many more cat videos to be sent around that, of course, the demand is huge. So, but if you make it in 1G on the ground, little crystals form as you extrude it. And of course, crystals, as you see here, are reflecting light, and so they would reflect the signal that you're trying to send down the fiber out, and that would that makes it useless at the moment. But experiments in parabolic flights have shown that you can make sections in microgravity that are without these crystals. But they're only a few centimeters long, tens of centimeters long. You need kilometers of this material, and that's what the three companies are investigating. Can they make many kilometers worth of this material, which only weighs several kilometers per kilogram in space. And again, it sells for so much that the cost of taking it up and bringing it back from space and having someone up in space making it for you is not important. And all of these uses for space will benefit from commercial space stations where you can just book space, a lab space, a room. The tourism is obviously part of this Axiom Space Ventures idea, because they've got Philippe Starck, the famous yacht and six-star hotel designer, to design their interiors. They look very spiffy, not at all like the hostel-like arrangements you get on the International Space Station. And all of these add up to customers. And those customers will want probably less Spartan conditions than the International Space Station astronauts. They might like toilets that really work and even showers. Well, that can be done, but it's liable to use up a lot more water, and it's expensive to bring that water from Earth. So maybe asteroids can solve that problem, and as the first thing they would do. Once we have some profitable in-space economy going, then as economies tend to, they will grow exponentially. And we won't be limited, our activities in space won't be limited to government programs anymore. They can be much larger, and they're liable to expand what we can do in space and lower the cost of doing it. Our capabilities in space right now are surprisingly limited. What can astronomers do to help? Well, large telescopes are needed to take large numbers of measurements for orbital measurements. You want a large telescope because these asteroids move away very quickly and get very faint within a week or 10 days. To get colors or spectra, even better, and to do it in bulk. Right now, we're finding, even without these new surveys, 2,000 asteroids a year, near-Earth asteroids a year. And the number that get any kind of characterization in terms of their colors or spectra, well, it's 100 or 200, something like that. It's very little. We're falling further and further behind. We could, at the Center for Astrophysics, have a neat instrument which can do X-ray fluorescence spectroscopy. These X-rays from the sun shine onto the asteroid surface or any rocky body, and they cause the material to fluoresce, and different atoms will fluoresce at different energies, and we can measure those and see what the surface is made of. And it turns out to be a very convenient little package. It's very light and compact, so it could go onto a fairly small satellite probe. But even better, it can be used to navigate the satellite by looking at millisecond pulsars, which are the best clocks in the universe. On its way there, they're X-ray sources, and they pulse very regularly in X-rays. And so you have that, and you can find out where you are to within a few kilometers in 3 dimensions. And you can find your velocity too from the Doppler shifts. So this is a very promising way of making many small spacecraft operable autonomously, and that's going to keep the cost down. Or of course, we could have another aerial like a spectroscopy mission designed for small bodies. And I think this would be a very strong proposal. Such a mission could do other things, high redshift gamma ray bursts and so on, but maybe we should try to sell it as a small body mission now. Anyway, there's lots we can do. I think once we set this up, we get into a virtuous cycle where the profits from our greed, the profit motive, will allay our fear, because there are 3 problems with this whole asteroid deflection business at the moment. One is, as I mentioned, the need to practice, and low cost will make that easier to do multiple times. Second is, if we find a killer asteroid on its way to us, we may only find it a year or 2 ahead of its impact time, and that's not enough time to start building a mission and launch it and get it there. But for one thing, we're now looking at many more launches happening per year, and we could, with this urgent need, we could probably preempt a spot on one, so it could be negligible waiting time. But even better, the low cost means that maybe we could pre-package deflectors. I don't think we would really want to put nukes in orbit indefinitely, but we could put a gravity tractor, or we could put a kinetic impactors on orbit in some convenient place where they could easily get at almost any location. And that would mean, for instance, a Lagrange point, the Earth-Moon L1 point, for example. And then they'd be ready to go. And then the problem with the kinetic impactors was how small the change in velocity was that it gave. But as we get better rockets, Starship in particular, we can send higher mass. That could go to the payload itself, or it could go into propellant, which would move to higher impact speeds. And that might be the right route because of half mv squared. And that would lead to a higher change in velocity. And so much fewer missions, maybe just one impactor would be needed. This is very hopeful. These same developments would be great gains for science, for planetary science, because we could have many more capable planetary missions exploring the solar system at scale, which is probably, instead of 1 or 2 missions a year, we might have 10 or 20 missions a year. And there are so many places we have not been to and been to orbit around, so many moons, the whole Kuiper belt, more or less, apart from Pluto, and Araroth has not been explored. And those were just flybys. And we could also store, again, at the Earth-Moon L1 point, for instance, missions that are ready to go. If we discover a comet coming in on a good orbit that we could match, we could go through it. Or even more excitingly, I think now, interstellar objects. We could actually visit some of those if we had, there's very little warning time there, but maybe if we had missions ready to fly, in orbit, ready to go, once we make a discovery, we could actually intercept some of these. So there's a great chance of improving not only fear, but love too. But for the normal astrophysicist, as opposed to a solar system person, and those, I don't know if you know that, but those are pretty different fields with separate centers of excellence, separate practitioners almost entirely. What is good about this? Well, again, the SpaceX Starship, high mass at low cost. The design of spacecraft in this new era where we can get high mass at low cost means we can assemble or manufacture even pieces of our spacecraft or our antennae on orbit. We can refuel on orbit. There are many plans and startups and tests of all of assembly and manufacturing are likely to happen very soon. So this is a chance to make spacecraft much cheaper and stronger. And have larger design margins. Right now, people worry about a kilogram of mass or even 100 grams of mass. And that means many design iterations to keep that mass down. That won't be important anymore. And that means design not only gets easier, it gets easier and therefore it gets cheaper. We could fly bigger solar panels because we have more mass available. And that means instead of operating on a 1 kilowatt, like a hairdryer level of power, the way the Chandra X-ray telescope does, we can move up, which demands very special electronics. We could move up to a much more power hungry but cheaper electronics and bring the costs down. This is very important. Again, because we can assemble on orbit, we can design spacecraft that don't need as much care to survive launch. So this is great for astronomy. For the radio and submillimeter, it means we can build giant dishes. We don't, for the far infrared through UV, we don't have to have this complicated folding up as we did with James Webb Space Telescope. We can just assemble on orbit in a much simpler way. X-ray telescopes will benefit from the larger diameter of the new rocket fairings and get much larger area. Gamma ray needs basically mass and size, and that's straightforward and should be a big win. But I think the biggest win will be in interferometers, mostly in the UV through near infrared. That will allow us to image supermassive black holes down to their event horizon and their environments, like the Event Horizon Telescope did in the radio, but now with many more diagnostic emission lines and so on that we can use. And high angular resolution is probably the area where we failed to make enormous progress the way we have in sensitivity or survey capability in astronomy in the last few decades. I think we're poised now to have a great advance in that area. And I don't know if you know this, but every 10 years in the United States, we have a thing called the Decadal Review, which tries to come up with a policy for what we should do for the next 10 years. One is about to come out. It should have come out months ago, but we're all on tenterhooks waiting to see what it will recommend. But the next one will be starting in 2028, and so only 7 years away. Some of these changes that I predict should have come into focus and be clearly applicable by the time they get started. So I think we could have a very different plan, a very different scene in astronomy in 2030. And so now I think perhaps you understand why I moved from quasars to asteroids, and some idea perhaps of the future of astronomy. Thank you.
Thank you, Martin. That was fascinating, from science fiction into what's just about fact now, I suppose. Before we get on to questions, can we ask people to unmute and thank Martin for his talk?
Okay.
Ian, do you want to read out any questions on Zoom, please?
Yes, there are a few. Can I start with one from me? Could you paint some of the killer asteroids so that the solar radiation pushes harder on them?
That has been proposed. I think it's also a very slow method.
Yeah.
It takes decades. So we typically don't have decades of warning, but that will change once we have those two surveys completed. So we could look at longer term, slower solutions for the more dangerous looking ones out of those surveys.
Okay. Next one is from Ron Rothammer, who's wondering, how do we know there are 900 Earth-crossing asteroids, and that represents 90% of them?
No, that's of Earth-crossing asteroids. That's 1 kilometer or greater size asteroids, which could be extinction level event impacts if they hit. And you know how many you found, and there were surveys for this particularly. You know where you looked, and you can model the solar system with asteroids and see how many you would have picked out from the model given the way you looked. And then you say, well, I found 900. How many must there be altogether? And the answer is about 1,000. And so we're missing 100. And none of the 900 yet are of that size of the near-Earth asteroids is a problem. It's not there. None of them are going to threaten Earth for the next few hundred years. But that doesn't mean the remaining 100 don't contain something deadly. Was that clear?
Well, it was Ron that asked the question, but yeah. John Murrow has a question. He wants to ask it.
Yeah, I've actually got two. The first one it's more of a statement than a question.
Mm-hmm.
One of the problems I think recognised with these missions that change the orbit of asteroids is that you can use them as a weapon as well, of course.
Mm-hmm.
You can actually change the orbit of the asteroid to hit your enemy's territory, though you'd have to know quite a few years in advance you're about to start war with them. But it's always been a possibility. And I just wonder what your thoughts were on that.
I do, in fact, talk about that in the book, along with a whole bunch of things. But basically, they're a terrible weapon, because you have, not only must you decide you really hate these people so much you want them dead a decade or two in advance, getting the asteroid to hit exactly where you want is really tricky. You're going to have accurate, ongoing control of this asteroid. And that's going to make it obvious that it's not behaving properly, and you're likely to be exposed as this evildoer long in advance, giving your supposed future enemy a chance to hit back at you. And an intercontinental ballistic missile is a much more effective and sensible tool to use if you want to destroy an entire country, but I hope nobody does. But you know, that it's just a silly way to use your resources. You won't hide, and it's very inaccurate.
Thank you. Shall I take the second one as well, which was about, you mentioned about putting a mission at L1 to actually chase a comet. ESA, of course, are about to put one at L2 in, I think it's 2029 it's launching.
You're right, I should have included that. Yes, it doesn't matter. Any Lagrange point is good because you can get, it's very easy to get from there to the rest of the solar system.
Yes, there's been a couple of recent talks on it. We ought to have one here as well, actually, Mark.
Yes, it's a great idea. And they of course could also go to an interstellar object, and the Rubin telescope will probably find one interstellar object per year is the current estimate.
Yes, I think they said, I think Colin Snodgrass said there was a 5% chance.
Okay.
And the other 95, they'll have to choose something that's in the solar system, either unknown or known. The fallback is you choose, they've got a couple of things on the list saying these are known ones we'll go to if we've been there 5 years and nothing's happened.
Right, because you have a lifetime issue with any spacecraft.
Yes. Well, it has to burn fuel to go around L2 because it's not
stable.
It's not stable. So you use up a little bit of fuel, and then you need to, depending on how long it's been, apparently there's some very strange graphs about where you can go to for how long it's been and how much notice you get. Some three-dimensional plots that confuse everyone.
Yes. How much fuel do you have left, and what is the orbit you're trying to match is going to be.
And how much notice you've got in terms of years to do it. Yes. So
it's a complex problem, but it certainly would be a lot easier if you could afford to keep putting up new ones because they're so cheap.
Well,
keep your stock fresh.
This is cheap because it's hitching a live ride on another rocket that's already going to L2. Right. So the launch cost is virtually zero, or in practice is zero almost.
Yeah, I think launch costs are now going to be virtually zero for any mission because the Falcon Heavy is $90 million, and that's very cheap. And Starship should be even cheaper per ton. So I don't think launch cost is any longer going to be a bigger consideration in most missions anyway.
Thank you.
Sarah has a question if she would like to ask it.
I think she said, can you ask it, Ian, please?
Okay. It says, how do you think space mining will affect, if at all, the space environment itself and the chances of asteroid collisions on planets and potential planet evolution?
In a solar system sense, very little. Just taking an asteroid away won't change the dynamics of the solar system. If you mine it in its native orbit, and the orbit is one of these that crosses the Earth, then you want to be very careful to pick up all the tailings, all the debris from your mining operation, which will be far more, in most cases, than if you're mining water, you're going to leave 10 times as much water material behind as you take away. You should not leave that in, just let it float out in space, because it will gradually spread around the orbit and produce wonderful meteor displays, but could also take out satellites in orbit around the Earth. So I think you have from a commercial point of view, you have an insurance problem. You could be liable for several $100 million a pop on taking out one of these geostationary satellites. So you have to watch out.
And Graham Rule has a question. I don't know if Graham wants to ask a question.
I really enjoyed your talk, but all this talk of mining strikes me as you're being able to move. Even if you manage to extract all the platinum, for example, from your asteroid and bring it near the Earth, you still need a lot of equipment and energy to turn it into some sort of finished product. how do you get your factories up there to do all that?
Yeah, this depends on a space economy growing using initially material from Earth. So it could well be building, there's very likely to be quite a number of commercial space stations, I think. Axiom is only one of 3 or 4 companies that's very plausibly going to build them. They have a real contract with NASA. They will be putting a module on the space station soon, and they will, by 2025, and they will grow that to 5 modules or 6 by around 2028. And by that point, it will be they can detach and become an independent space station. There are others who wish to do it, and I think all those different users may well want their own space station. If you're really producing kilometers of optical fiber, then you probably want your own space station, or you want to rent a lot of space in at least. But probably there will be quite a market for growing space stations. And then is there something where you want to build structures in space out for commercial uses? And that's less obvious. There's obviously astronomy uses for building antennae. If solar power beaming to Earth matter could be made, yeah, I know, could be made commercially viable, then maybe that would be a reason. I don't immediately see a way that's going to happen. Could be the US Navy seems interested, though. They've been practicing with their X-37 space plane the microwave transmission of power in space. So maybe there's some application beaming power to ships on the oceans for some reason. I don't know why you do that. I know the US military has talked about sending power to war zones where it's dangerous and very expensive to send lorries with tanks of gasoline. But also disaster situations where it's also hard to get contact via the ground. You might find ways in which you could make a viable system. I've got off track really rather. My bet is that people will find things they need to do once you have a commercial setup going, and we'll start building things in space. There may be infrastructure for a space station that you'll no longer have to send up all the parts from the ground. You could make some of the parts in orbit. We'll see.
Okay, that's all the questions from the members.
Okay, I've got a couple here on YouTube. We have quite a big audience on YouTube, over 60 people.
Oh, great.
From India, USA, Romania, various places all over the world.
Great. Thank you for watching.
And lots of positive comments about your talk. I think it's brilliant. One about what about water mining? Since you're mining water on asteroids, could you use heated water, steam powered effectively, to divert the asteroids? Is that a possibility?
Yes, that makes sense. I don't think anyone's really looked at it. The problem is water rich. What we're probably going to be hit with is a stony asteroid that's very dry, because the odds are in its favor. Only 1 or 2%, what was it, 3 or 6%, depending on whose estimate you use, of all near-Earth asteroids are water rich. Right, so it's that. So if we were lucky enough to get hit, be threatened by one of those, then you could go there and use a steam rocket. Yes.
Okay, and something that's not directly related to the talk, but has an effect on it. It's something that we've had a major event about in June. It's about these mega constellations that are being launched, and about regulation of that. Obviously, with the amount of stuff that's going to be up there, that's obviously going to affect asteroid mining as well. What are your views on that, about regulation and all these mega constellations?
Oh yes, one of the big messages from the book is that you tend to think of space as a place for engineers and scientists, and really, if there's going to be a space economy, we need lawyers, businessmen, and many policymakers and legislators and diplomats, and a vast range of skills that are not traditionally associated with space. And I mentioned lawyers in front of my normal science engineering type audience, and they cringe and say, do we have to have lawyers, you know? But yeah, you do. You don't want to live somewhere where there are no lawyers. That is not a pleasant place to be.
Yeah. Okay, I think that's all the questions we have on YouTube as well. So can I ask everyone to unmute and thank Martin again for his talk?
Thank you. Thank you. Very nice.
Really good.
Very
Thank you very much, Martin. I'll just share my screen again as a reminder of what's coming up next for us. Hopefully you can see that. So our next meeting is on the 5th of November about the accretion disks of stars, and that will be a physical one in Edinburgh. If you're in Edinburgh, come and join us at the Augustine United Church on George IV Bridge, but we'll also stream it online on Zoom for members and on YouTube as well. And I'll pick up what we're doing his comprehensive What's in the Sky in November as well. So with that, thank you very much. Thank you, Martin. And thank you everyone for joining us wherever you are in the world. Hopefully see you again. Good night.
Thank you. Bye-bye.